So today, if you'll excuse the exaggeration, we're going to listen to the sound of atoms and molecules bonding. So on this screen, what we have is a sample on which we've got some molecules and atoms, and we have a tip. The important thing here is that we've got a very reflective sample, and you can see the reflection of the tip in that sample. It's a piece of silicon. Let me show you what it looks like. So that's the piece of silicon, very much like this. So maybe it'd be just a heck of a lot easier if I bring out this demo. So what we have is we have a tuning fork, right? So it's a quartz tuning fork. Actually, you've very likely come across these before multiple times, but you didn't realize it. In every quartz watch, in every quartz clock, inside there, the timing element is one of these things. It's a tuning fork that vibrates up and down at 32,000 times a second, or roughly 32,000 times a second. And that acts as the clock, that acts as the electronic component, or the electromechanical component that gives you the timing. What you can do is you can take the tuning fork out of the can, and you can glue a tip onto it.
Or blue tack.
Oh, you can, yeah, perhaps not, in the real case we don't blue tack it on, we actually do glue it on, but actually the gluing is probably just about that accurate. So what you have is a resonant frequency there. There's a particular frequency, natural frequency, this wants to vibrate at, which depends on the density and depends on the length of the tuning fork and all its sort of material properties and its structural properties and its geometry. But the really important thing then is if you glue a tip onto the end of it. Okay, so let's get it resonating again. So you can see tips resonating, tuning forks resonating. We bring it in on top of an atom, and the interaction between the atom at the end of the tip and this rather oversized atom or molecule on the surface changes the force between the tip and the sample, and that changes the resonant frequency.
So Phil, when the tip approaches the atom,
yep,
what is it about the atom that is affecting the tip and therefore affecting...
Brilliant question. It's forming a chemical bond. Basically at the level we're looking at here, there are a range of different forces. Electrostatic charges, for example, you can even have magnetic forces. But what we're really interested in and what this experiment is all about, and the experiments we've been doing of late are all about, is getting right down to that regime where it's the overlap of electron orbitals, it's chemical bond formation at the single bond level. So the state of the art with these techniques, with these scanning probe techniques, is we've gone well beyond atomic resolution. We're now at what people call subatomic resolution or single bond resolution. So all of this is happening. So we did a video. It's actually almost 3 years ago, isn't it? So we did the atomic switch video, I think. Certainly 2 years ago. So it's happening in the same system which we did the atomic switch video on. And I'm sure Brady will kindly put a link to that video somewhere. It needs all the publicity it can get. So it's happening actually in here, in this system. So this is an ultra-high vacuum system. The pressure, as you can see, is 1.6 by 10 to the minus 11 millibars. 14 orders of magnitude below that you have below atmospheric pressure. Well, this is what the data looks like in real time. So what we're looking at here is the underlying silicon surface. It's actually, just to clarify, it's actually a mixture of silicon and silver, but this is our substrate. This is the surface on which we've put our molecules.
That looks very ordered.
It is extremely ordered. That's, and you can see the individual atoms. Over here, these sort of grain-like structures are assemblies, islands, a single molecule thick.
They look like puffed wheat.
They do look like puff wheat, indeed. They do look like puff wheat. You can see their differences sort of in the orientation. And the molecule we're looking at now is this pretty simple molecule. We're physicists, we like simple molecules. Once it gets above, 20 or 30 atoms, I get very confused. Each one of these black things is a carbon, but for NTCDI, on both ends of the molecule, this atom is replaced by nitrogen, and we have oxygens hanging off here. And what we're very interested in is, because you've got the nitrogen and the oxygens and the hydrogens on this, we're really interested in probing hydrogen bonding, and that's really what the focus of this experiment is. Hydrogen bonding is the type of bond that holds our DNA together. What we do is we take this frequency, this resonant frequency, which if this tuning fork here on which we've got our tip was bigger, we could actually hear this. In fact, it turns out that the resonant frequency of the tuning fork here, the actual real thing, is about 25 kilohertz, which is not so far off the audible range, the limit of human hearing, which is about 20 kilohertz. For me, it's much, much worse. My hearing is scrambled from playing too much guitar, so I can't really hear much above 15 kilohertz. What we do is we take that resonant frequency and we look at how that changes as we move the tip across the surface. So we measure that resonant frequency directly, see how it changes. And the way in which it changes tells us about how the tip is interacting with the atom at the surface as you move it across. The fact that you're moving back and forth between atoms means that at some places you're directly over an atom, or more importantly, directly over a bond. You get a strong interaction, you get a bigger change in resonant frequency, and then you move to a place between atoms, or a place where there isn't a bond, a dangling bond, a bond sticking out from the molecule, and you get a weaker interaction, so you don't see as big a frequency shift.
What force is acting on the tip?
The chemical bonding force, yeah, it's a force of a chemical bond.
So the tip's just being yanked towards it or pushed away?
It's very interesting. This is the great question, because if you use, for example, silicon for your tuning fork or your cantilever, then what happens is that the tip will get yanked in. And that's not what you want, because you go smack into the surface and you ruin your surface and your tip. The great thing about these quartz tuning forks is that they're very, very stiff. They're about 100 times stiffer. So that means you can get these very, very small oscillation amplitudes and bring it in very, very close indeed without it snapping in and without it ruining your surface. And I should also point out, again for the experts, I'm always conscious that there are people out there who will fill the comments board, oh, I didn't say this and he didn't say that and why did he miss this? Important thing here is that what we actually do in the experiment is we tie that tine down. We tie one tine down and we're only relying on this one. Let's get to the sound. So what we are doing is we are taking that signal from the tuning fork, which in principle we can either map out like this or we can listen to. And that's real time. As we go across every scan line, this is the change in the frequency as we scan across each line of the image. And what we do is you can convert this change in frequency. What you can do is just say, well, this lowest point is going to be black or dark red, this highest point is going to be white, and then scale it. Or we can do what we're doing here, and we can listen to it. What this little box is doing is actually from our first year lab, and we spent a lot of time, myself and a PhD student called Julian Sterling, thinking about how we're going to do this, how we're going to convert this thing. The last time you were here, Brady, you might remember you sat over there for an hour while I tried to write a piece of code and it didn't work. Then we thought, well, we might build our own electronics to do it. And then suddenly I thought, well, usually when I'm stuck, what do? I go and ask George. So I went and asked George, and he says, yeah, you want one of these. And so what this box is doing is it's converting this value of the frequency shift into a signal that we can hear. It's basically transposing it from 25 kilohertz down to a signal that we can hear. We can change that center frequency as you like. So in that sense, it's artificial. But to a certain extent, it's no more artificial than what we've got here.
So what's the title of the video?
I would love to call it the sound of atoms bonding, but that might be a little bit misleading.
Are they bonding, or have they already bonded?
So when I talk about the sound of atoms bonding, we'll do another experiment on this. I mean the atom at the end of the tip bonding with the atoms at the surface. That's really.
Are they then unbonding?
Yeah, that's exactly it.
So this is like a really promiscuous bond. Now.
That's exactly it. So it's going bond, unbond, bond, unbond, bond, unbond, and it depends on the oscillation amplitude. So in some cases you could have this as much as 10 nanometers. So here's your bond, and you're swinging all the way up and then coming back down, making the bond, swinging all the way. What we tend to do, and really if you want to measure those hydrogen bonds and see them directly, is that you keep this very, very oscillation amplitude very, very small. So you're always sort of within that bond-making regime. Quite a few scanning probe people would look at this and go, that's a bit of a gimmick. But in fact, it was one of my heroes, a guy called Don Eigler and his group in IBM Almaden, who were responsible for pioneering, single atom manipulation. This is what they do when they're doing manipulation of atoms, pushing atoms around. They listen to the signal that's coming back as well as looking out on the screen, because your ear sometimes is more sensitive to changes, and also this is at a slightly higher rate than these lines appearing on the screen, so you're more sensitive. And that's what science is all about, is trying to invoke as many of the senses as possible to make sense of the data. Oh, that's my little Marshall amp. Unfortunately, it's I've now used this thing called Guitar Rig to play guitar, so the Marshall amp has sort of fallen into disuse a little, so I think it was feeling quite lonely, so I decided to bring it down, and plus it's Marshall.